Okay, good morning. So this assignment is about exponential functions in context, specifically also using the symbolic representation. Now we will have another lesson this week about factoring, but this is the main lesson for the week. So remember, just with exponential functions, first, when we have symbolic representations, we use function notation, which involves inputs and outputs. That's described down here. And specifically for exponential functions, we have the initial value and we have the constant ratio. So this is the assignment, and there are 4 questions, but I'm going to do the 4th question, which is actually the most challenging question. So I'm going to just go through it and just follow along. Now pay attention how I'm going to refer to the constant ratio and the initial value. Okay, so let's see. I'm just going to read this. There are numerous videos on YouTube showing someone who made a very creative arrangement using hundreds of dominoes. Then knock just the first one over to see what would happen as the rest of the dominoes topple over sequentially. Usually the dominoes used in these videos are all the same height. However, they don't have to be. Domino can knock down a subsequent domino that is up to 1.5, 1.5 times larger than itself. In other words, 3 halves as large. For example, consider a 4-inch tall domino. 1.5 times larger than 4 inches is 1.5 times 4, which is 6. You can also think of it like this. Because half of 4 is 2, then you add the amount onto 4. 2 plus 4 equals 6. Therefore, a 4-inch tall domino can knock over a domino that's up to 6/3 inches tall. Consider a sequence of dominoes such that the first one is 1 inch tall and each subsequent domino is 1.5 times the previous one. Let d of n be the height of the nth domino. Okay, first, before I start, I noticed right here, is let d of n be the height of the nth domino. So n, the input, is the number of the domino. D of n, the output, is the height of that domino. So I'm just going to, right, knowing that information and knowing that each domino can be or is 1.5 times the previous one, I'm going to use that information to answer the question. So first question here. Says determine the value of d of 1, explain that means in the context of the situation. Well, d of 1 is the first domino. They tell me the first domino is 1 inch tall. So d of 1, the height of the first domino is 1. In context, this means the height of the first domino is 1 inch. Then they say determine the symbolic representation of d of n. All right. So first, I know that the constant ratio is 1.5. How do I know that? Tells me up here it's 1.5 times. So it's going to, so the a value is 1.5. That means d of n, I just plug that in, equals the initial value times 1.5 to the power of the input, which is n. Not 1.5, 1.5, not 1 divided by 5. Okay. If you want, you can put the constant ratio in parentheses to make it a little clearer. I say, okay, I'm going to solve for n, c. I'm going to solve for c. So I have this one value up here. When the input is 1, the output is 1, right? So to find the c value, I have to figure out when it's 0. So when the output is 1, I'm just plugging in c times 1.5 to the power of 1. Well, anything to the power of 1 is just the same number. So c times 1.5 And with variables, if you write nothing, that means times in between the number and the variable. So I divide by 1.5. So I get C equals 1 divided by 1.5, which is, see, you could figure it out longhand or use a calculator. 1 divided by 1.5 is, oh, that's 1/3. So you have 2/3. So I'm just going to write that 2/3. It's easier to write. So my symbolic representation, the answer is B of n. B of n equals 2/3 times, and I'm going to change everything to a fraction. So again, 1.5 is the same as 3.5. So again, you can see how it's easier to use fractions. So I do encourage fractions. Decimals is fine, but notice sometimes it's easier to write a fraction than a repeating decimal. All right. So that's the answer to that one. Next, determine D of 10. Explain what that means in the context of this situation. So now that we have the symbolic representation, we can find D of 10. How? We take the symbolic representation over here. This number is so this value is very important. This is our answer. And we just plug in 10 for n. So let's write that in here. 2/3 times 3/2 to the power of 10. So what is that? 2/3 times, I take 3/2, which is 1.5. So then I do to the power of 10. All right, that number. And if I want to write it, I could write it here like 57.665. But basically what I do is then I take this number, multiply it by 2, divide it by 3. So I'm going to round it to 3 decimal places. So 38.4336. 38 point, what was it? 443. So it asks, what does this mean in this situation? Well, I remember this means the input is 10 and the output is 38.433. So the input is 10. Input is the number of the domino. So this is the 10th domino. This is the output, and it's the height in inches of that domino. So we can say in context, this means the height of the 10th domino is 38.443 inches. All right. So now we can actually describe a situation using our symbolic representation. So for this next question, it tells us the Loha Tower is 184 feet tall. Determine the height of the Loha Tower in inches. So we can say, all right, it's asking, make sure you understand the question. What is the height of the Loha Tower in inches? Well, there's 12 inches in a feet, so I take the number of feet, 184 feet, and I multiply it. There are 12 inches per foot, right? 184 times 12. Again, you can write it out. Write it out to solve it. If you can, I would write it out, but I'm just going to use a calculator for this. So 12,208. So 12,208 inches. So the Aloha Tower, let's capitalize because it's a name. Aloha Tower is 2,208 inches tall. All right. So Molly is an engineering student at the University of Hawaii at Manoa, and she's curious about how many dominoes it would take if she started with a domino that is 1 inch tall and set up a sequence of dominoes that would be able to knock over a final domino that is the same height as the Aloha Tower. Use your function dividend to determine how many dominoes Malia would need to set up in order to knock down a final domino that is the same height as the Aloha Tower. So we can, in other words, the output is what we're given. We're told the height of the Aloha Tower. So we can actually still use the same symbolic representation. We know the output is 2,208, but we don't know the input. So I'm going to write out my symbolic representation. 3/2 times, I think this is 2/3 times 3/2 to the power of n. So I don't actually know what that is. So what I'm going to do is I'm going to take some guesses. So it's clearly taller than this. It's taller than 10. So let's see. I'm just going to take some guesses. So 3.5 times 1.5 to the power of 20. I'm going to try 20. Oh, 20 is about right. Let's see. Let's see if I do that again. Oh, that was a good guess. Okay. Times, and I'm going to go 1 less to the power of 19. That's less than, so it has to be more than that number. So I happen to guess the correct answer. The answer is 20. Is 20 equals 20? Why? Well, d of 20, I just used the calculator to calculate it. Let's write it out again. 20. That is not correct. 2 divided by 3 times 1.1.5 to the power of 20 is this number. So I'm going to write that out. Oh, you can't see the calculator. I just realized that. Well, just know that I'm doing 2/3 times 3/2 to the power of 20. I use a calculator to solve it, and I get, whoops. Whoops. Okay. Get 2,216. Okay. The 20th domino could be tall enough to be the height of the Aloha Tower. I know this because the domino could be taller than the tower based on the symbolic representation. All right. So this question is a bit more in depth than the other, but notice the basics are the same, right? Once we know the constant ratio and the initial value, we can find any number of dominoes. right? We could even find how tall a domino would have to be the height of the Aloha Tower, or even taller, maybe the Empire State Building. How many dominoes would that take? Or we could calculate with our symbolic representation. So that's one reason it's useful. We could just check any value you want. Notice I didn't have to go one by one. I just skipped to the value I wanted to check. Okay. So again, for each question, they're going to be using function notation, which we talked a lot about, and our symbolic representation. So just do your best. We will talk more about this later. Please ask if you have any questions. And remember to always think about your initial value and your constant ratio, which are the two parts that define exponential function. There's also the input and the output, which is very important. Input, and the entire thing is the output. And then just go through all the questions. All right, I will have a good rest of your day, and I will talk to you next time.